The very last entry in Table 8.1 is what we call a beta-gamma controller. It is also called a controller with proportional and derivative mode weighting. To understand why we might want to use a controller designed like this, let's look at one phenomenon called kick. So suppose a process is operating at a steady state where the measured value of the controlled variable is approximately equal to its set point, and therefore the error signal is approximately 0. What happens to the error signal when the set point is changed? The way that the set point would be changed is that an operator might sit down at a computer terminal and change the value in a field from 10 to 11 and then hit enter. If the set point is instantaneously changed, then the error signal also instantaneously changes to a new value. When that error signal instantaneously changes, there's a step input in the error signal in the proportional component. This causes the controller output to suddenly change to a new value. When the controller output suddenly changes to a new value, the pneumatic signal going to a control valve may cause the control valve to pop partway open or partway closed. However, when the error signal suddenly changes, the derivative component goes to plus or minus infinity, because the derivative of a step is plus or minus infinity momentarily when the step occurs. Remember that the derivative of a step function is the Dirac delta function. Therefore, the derivative component of a PID controller will momentarily send an infinite signal, or at least a maximum signal, to the final control element. These phenomena are called proportional kick and derivative kick. Kick can be damaging to mechanical components in control loops, and it can also cause sudden disruptions in process behavior. So often we want to reduce or eliminate kick, and we can do this by redefining the error terms, so that the error in the proportional component is some fraction of the set point minus the measured value. The error in the integral component is defined as usual, and the error in the derivative component is some other fraction of the set point minus the measured value. The fractions are the beta and the gamma terms shown here. Beta and gamma can be set to very small numbers, or even to 0, so that when there's a set point change, the proportional and derivative elements have no response. But when the measured value changes, the proportional and derivative elements do respond. So beta and gamma provide what are called proportional and derivative mode weighting. If they're set to 0, then changes in the set point have no effect on the proportional or the derivative components of the controller. And that means that when the set point changes, it is only the integral component that responds. However, if the measured value changes and the set point remains constant, all three components can respond. Up to this point in Chapter 8, we've considered what we would call analog controllers, assuming that all of the signals are continuous in time and that they can take on continuous ranges of values. But in fact, many controllers used commercially are not analog controllers, but are digital controllers. And digital controllers use signals that are discrete in time. That is, they're not continuous. They're measured at discrete time points. And the measurements are sampled at an interval we call delta t. For digital controllers, the integral mode and derivative mode are defined differently. The integral mode is defined using the sum of discrete values of the error signal. And the derivative mode is found by using a 2-point backward difference approximation for the derivative, in which the error from the previous time point is subtracted from the error at the current time point and then divided by the sampling time interval delta t to obtain an estimate for the derivative. Therefore, the parallel PID controller equation for a digital controller has a sum over past error signals and a difference between two error signals for the integral and derivative forms, respectively. We call this form the position form of the digital PID controller algorithm. Now, it turns out that this summation term that's used to approximate the integral element can be problematic. If there is a large sustained error, the controller output may saturate, that is, it may go to its maximum or minimum value, and the integral term may remain large until the error changes sign for a significant amount of time, so that the opposite sign error can cancel out the large contribution from the original error. This phenomenon is called reset windup, and in fact this can also happen with analog controllers, and there are algorithms that are used to deal with reset windup in the analog case. But for digital controllers, one way that we can deal with reset windup is to use what's called the velocity form of the PID controller algorithm. While the position form calculates the value of the controller output, the velocity form only computes the change in the controller output from the previous value. To find the change in the controller output, we calculate the controller output at time point k and the controller output at the previous time point k minus 1. The difference between the integral terms here is that at the kth time point, the integral is summed from j equals 1 to k, and in the k minus 1th time point, the integral is summed from j equals 1 to k minus 1. For the derivative elements, we simply need to decrease the index by 1 on the two terms that we're taking the difference of. Then, to find the velocity, that is the change in the controller output from the k minus 1th to the kth time point, we subtract these two equations. Notice that when doing this, we eliminate the summation, so there can be no reset windup. The controller tells the actuator by how much to move and not to where to go. For analog controllers, there are other methods to deal with reset windup. Now, if we use the velocity form of the PID controller algorithm, it's important to note where the set point is. Remember that the error signal at e sub k minus 1, and e sub k minus 2 are all the set point minus the measured value. Therefore, the set point is going to cancel in both the proportional and the derivative parts. That is, the set point only influences the integral part, so using the velocity form of the digital PID controller algorithm may also eliminate proportional mode and derivative mode kick when the kick arises from set point changes. But if the integral part is left out, disturbances can cause drift away from the set point. The digital form of the PD controller algorithm without an integral part does not contain the set point. The same is true for a beta-gamma controller when beta and gamma are set equal to 0 and the integral mode is also set to 0. Usually, a feedback controller is designed to keep a controlled variable at its set point. That is, we want to keep the error signal close to 0, where the error signal is defined as the set point minus the measured value of the controlled variable. The vast majority of controllers that are used industrially are some form of the PID control algorithm or perhaps an on-off controller. The sign of the controller gain, Kc, determines whether the controller is reverse acting if Kc is greater than 0 or direct acting if Kc is less than 0. The P, I, and D elements respond to the value, the accumulation, and the rate of change of the error, respectively. Modifications of the PID control algorithm can eliminate undesirable control loop behavior such as proportional and derivative mode kick and reset windup. Back in Chapter 9, we said that feedback controllers should provide negative feedback to ensure that processes are stabilized by the introduction of feedback control. In order to provide negative feedback, the product of all of the gains for all of the components in the control loop, including the process, the sensor transmitter, the controller, the final control element, and any transducers that might be in the control loop, the product of all of those gains must be positive. Selecting a reverse acting or direct acting controller for a feedback control loop is always done to ensure that the product of the gains is positive so that the feedback control loop is stable.